now in Berkeley is writing a paper about this. I hope so, because I thought the paper should have already submitted last. I didn't see it. Okay, anyway, there is a PhD student who should rely on this to graduate. Okay, anyway, yeah. So this is good. This is good. And in this year, and then there were a lot of follow-up observations in those days. And we also tried to narrow down the error of the location determination. So there were a lot of exciting effort during those days. Quite good, quite good. All right, so eventually it will land somewhere, right? So where will it land? Difficult to tell, right? Yeah, hopefully it's still on the Earth. Yeah. Okay, so this is the parachute. So this is after landing, and our gondola somewhere. So this looks like Mars, isn't it? So it landed on Mars. How come? Well, of course it's not. It's not. Yeah. So we went there to recover all the things. Yeah. Where is it? It's in Peru. It's in Peru. So this is the how you can see New Zealand. New Zealand here. And after launch, it went to the west, and then turn around here, and really take a circle around the Earth, and it took only, I think, 14 days to have this run, 14 days only, and at that time, because it already surrounded the Earth once, CSBF actually declared successful flight. It looks like they want to terminate at that time. Yeah, they say, oh, it's already successful. Yeah, but anyway, it keeps going, and somehow it spent a lot of time here, but it's good, so that we discovered the GRB. Yeah. And then in early July, we decided to cut it down. Actually, we decided to cut it down when it was still here, and somehow it doesn't want to go to the land, because at that time we decided as soon as it goes up above the land, we will cut it down, and then it spends maybe 1 more week after our decision. Okay. Anyway, the reason to stop the mission again is there was a leak. Still, there was a leak. But CSBF people were already quite happy because it's already after 47 or 46 days. And we have a lot of monitoring data to see the altitude, the day and night change, these kind of things. And they think that it's already quite good, and they want to study more to figure out what went wrong. And yeah, so that sounds reasonable, so we also agreed to terminate the mission. So that's why it landed in Peru, and Peru is also an okay country for those Americans to recover it. Okay, yeah. So at the beginning, actually, we were kind of worried when we cut down the mission above the ocean. That would be much more difficult to recover. Still possible, but much more effort. Yeah. So we are now analyzing the data. It's 40-some days, so there are a lot of data. And of course, this GRB is a major thing. And I'm eager to see the paper draft, okay? And then the galactic center, because as I show you, galactic center, the elevation angle is good. Actually, we need to see the whole exposure map of the sky. But galactic center is good, with very good exposure. And also some other sources like a black hole, like AGN and some SGR event, and also pulsars. So we are now preparing for the next flight, and also working on new electronic systems, because as you saw in my earlier pictures, the electronics is huge. The car cage is a large one. For each detector, we need to have a car cage inside which there are 10 balls. And that's heavy, that's power consuming. So we now reach we are now working to make all these things smaller. We want to make most of them into some ASIC form, and in that way, then we can have small volume, lightweight, and low power consumption thing, so that we can really go to the space, right? So you can check COSI NCT for more pictures if you like. So that's it. We're now working for a future COSI-based space mission. So that's my talk. Thank you.
Congratulations.
Thank you.
This is wonderful. Yeah.
Especially in light with some quote-unquote unfortunate history. Yeah, this is wonderful. And I think a byproduct is the proof that these new high-pressure balloon is indeed now working. Yeah, that's very nice. And I think your choice of 500, 0.5 MeV energy range is very meaningful and clever, which covers many different physics or astrophysics. Congratulations. Now, before I came back to Taiwan, I used to be a member of a similar project called LIGO, Pogo Light. And and another one was a ground-based Compton telescope.
Ground-based?
Ground-based.
I'm sure.
What was the name? But anyways, do you have any comments on or comparison to other, especially in light of, it's kind of your in response to your earlier comment. What is the advantage of your hardware design that makes your smaller instrument comparable in sensitivity to the much bigger one?
Okay, thank you. First of all, I should make some correction because Bison mentioned balloon. I didn't want to emphasize on balloon, but the balloon that we use in this year's flight was actually a zero pressure balloon. Zero pressure balloon. In our previous flight, it was the usual conventional non-zero pressure balloon. Oh, sorry. We have super pressure balloon. Yes, that's right. Previously, we have zero pressure balloon. That's conventional one. And then the New Zealand flight is super pressure balloon. Yes, Peter mentioned that. And this is important for NASA because they want to develop this kind of technology to have super pressure balloon. There are some advantages. Okay, so that's one thing I didn't mention in my talk. Okay, and as for the reason of the increase of sensitivity, there are many factors put together because the data reconstruction analysis is complicated. So the reason to increase the sensitivity is that one is that we have a larger acceptance angle for the scattering event. That's one thing. For the previous COMTAIL, the photon must scatter to the downward direction. So that already limited the number of photons. But this is not really most important one. The most important one is that we have multiple scattering events in the detector volume. 3 or 4 interactions in the detector volume. This is important because you have more interactions, so that can constrain better your reconstruction. You have more constraints. And then also, we can determine the location of the interaction quite precisely within, say, 2 millimeter cube. That's also important for the event reconstruction. And also, energy is another issue, but energy which we cannot control much. The energy restriction is roughly 2.5 keV. We cannot control much. But with multiple events and also the small error of interaction location, then we can determine the direction much better than before. In this way, we can get rid of a lot of backgrounds. Because if you want to study crab, then you can get rid of other events. So in this way, background can be significantly reduced. We do some spatial cut when we want to have an image of some direction. And in earlier flights, in earlier missions, it's not easy to get rid of those backgrounds because the determination of directions is not accurate enough. I think that's the main reason. Yeah, that's the main reason. Yes. Yeah, thank you very much.
Also cost down also. Yes, also.
Cost.
Yes.
Yes,
Big
yes, that's big. So you need a large satellite, a large rocket, of course. And for the instrument itself, maybe I'm not sure. I'm not sure how expensive it was. I can't tell. Yeah.
Any other question?
Maybe quick one just to follow it up. So you mentioned there are also ongoing several other groups have efforts in the future instruments. So how different are their design or this similar?
Quite different. I did not prepare any material, but the detector design is quite different. Some groups actually use liquid, some material, liquid. And also silicon is also used. Silicon and some xenon gas and liquid PR something. They have different detector material. And, but somehow I do not see their progress. I only read the reports a few years ago, and I didn't hear any news from them. So that's strange.
No question. I have a question. Can you tell me about more about the how to measure this polarization using your detector?
Oh yes. Polarization measurement is that okay. For Compton scattering, if the incoming photon has a certain polarization, then there is a preferred direction for the photon to be scattered. There is a preferred direction, which is probably perpendicular to the polarization. It's not parallel, it's maybe perpendicular. Anyway, there is a preferred direction. So if you have enough events, then from the same source, you have events from the same source, then you can see, you can check the distribution of the scattered direction, the photon scattered direction. Then you can determine their polarization. So basically it's like that. But it's not that easy. You do need to have enough photons. Because when I say preferred direction, it doesn't say photon will go there every time. Of course not, right? It's just the cross-section has angle dependence. That's it. So you need to have enough photons.
Have you tried to see the polarization for that, the GRB event?
One student is now trying, but I'm not optimistic.
Yeah, two comments. One is that in the case of POGO, the way of detecting the polarization is like plastic tubes. And so it's kind of a honeycomb-like detector. And about the GRB relation to the half MeV or electron positron annihilation photons, I had a model for GRB, theoretical model for GRB, which relies heavily on the electron positron plasma annihilations in the atmosphere of GRBs. So such a detection is really keen to my interest to see if there's indeed associated spectral line.
POGO works in low energy range, if I remember correctly. Not really.
Not half MeV. Of the order maybe 100 kV, 200 kV.
No further questions?
I have several questions about the detection of the gamma ray bursts. As I know, the short gamma ray bursts will fade away very soon. So I don't know whether there is any technical mechanism that when the balloon flight detect gamma ray bursts, so the people on the ground can also note this event almost simultaneously at the same time. Furthermore, another question is that about the gamma ray burst event you mentioned in your talk, can it also be detected from the Fermi GBN monitor? Yeah.
Okay, so first, of course, we almost noticed the event right away because the data, we receive data in real time, and then there is a program running all the time, and if it happens in the night time in Berkeley, someone's mobile phone will ring. Okay, and so roughly we can do it this way. And Fermi GBN did not detect this one. Yeah. But SPI did.
Okay, so let's, it was a very wonderful talk. Actually, so I hope, there's in future you want to bring more exciting news. Okay.
Yes.
Okay. Let's, thanks to the speaker again.
Thank you.